Welcome back to the deep dive. Today, we are going far, far beyond the sunlit surface of the ocean. We're plunging into the abyssal zone. The abyss.
It's a realm of permanent darkness and just crushing pressure. We're talking about a zone that stretches from about 3,000 meters all the way down to 6,500 meters.
It's the single largest habitat on Earth. It covers roughly half the global ocean floor, but it's also the place we understand the least.
It really is one of the final frontiers on our own planet. And our mission today is to, unpack this extreme domain.
We're going to trace the geography of what is, surprisingly, the planet's flattest surface.
Right.
We'll reveal these bizarre chemical food chains that sustain life down there, explore the history of the pioneers who broke that pressure barrier.
And finally confront this growing tension between deep-sea discovery and, well, potential industrial exploitation.
So let's start with that challenge, the physical environment itself.
Yeah, and when we talk about depth, we're really talking about pressure. At these abyssal depths, a pressure can peak at around 600 atmospheres.
600, how do you even put that into perspective for people?
Okay, try this. Imagine trying to hold up the full weight of a fully loaded cement truck
Wow.
with just your thumb. That is the kind of force that every single organism, every exploratory vessel has to withstand down there.
That's just insane. All right, let's jump into it. Section 1, the geography of perpetual night. Because I think when you picture the bottom of the ocean, you probably imagine these, jagged mountain ranges, deep valleys.
Exactly.
But the reality of the abyss, especially its geology, is the first big surprise.
It absolutely is. I mean, our surface world is all about light, warmth, change. The abyssal zone is the opposite. It's defined by extreme darkness, a constant cold. It just sits there at around 2 to 3 degrees Celsius.
Freezing.
And just absolute stability. But you're right, the most counterintuitive feature is the abyssal plain.
Which are, amazingly, considered some of the flattest places on the entire planet.
Flatter than any desert or prairie you can find on land, by far. Geologists have this rule. They require the plains to have a slope ratio of less than 1 to 1,000.
Okay, so incredibly flat. But that's not just a fun fact, is it? That flatness is crucial.
Oh, it's vital. It's what allows unique phenomena, like the widespread formation of those deep-sea mineral nodules, to even happen. It directly links the geology to the modern conflicts we're going to talk about later.
So the sheer scale of this is just overwhelming. This bottom territory accounts for something like 40% of the entire ocean basin floor.
That's right, and it's especially vast in the Atlantic and the Indian Oceans.
How does nature even create a surface that is so consistently smooth and flat?
It's a burial process, a very, very slow burial process.
Okay.
The flatness comes from these thick layers of sediment being gradually laid down. It comes from two main sources. First, you have these dramatic periodic events.
Like underwater landslides?
Exactly. Turbidity currents. They're these dense, sediment-heavy flows of water that just surge down the continental slopes and then spread out, carpeting everything.
And the second source is that slow, continuous feed, right?
That's it. The steady rain of biological material falling from the waters above. We call it marine snow. It just settles and evens out any little bumps or irregularities over millions of years. It's like the ultimate geological spackle.
But that smoothness isn't perfect. There are things that break up this plane.
Oh, yeah. The plains are interrupted by the planet's tectonic activity, so you find the deepest trenches where one plate is sliding under another.
Subduction zones.
Right. And you have the mid-ocean ridges. Those are the volcanic seams where new crust is being formed. And then just scattered across the plains, you have seamounts, which are basically individual underwater volcanoes.
That brings us perfectly to this idea of the deep-sea energy paradox. If the entire abyss is defined by perpetual night, no sunlight at all, how do you sustain any life?
That's the fundamental question. And the primary answer for most of the life down there is an energy transfer from above.
Delivered by, what did you call it, marine snow?
Marine snow.
Yeah.
It's a term the explorer William Beebe coined. It sounds beautiful, but what it actually is...
It's probably less beautiful.
It's a continuous cascade of organic detritus. It's a mix of everything that dies or sinks from the sunlit waters, dead phytoplankton, bits of zooplankton, fish scales, and, a lot of fecal matter encased in mucus.
So it's sticky.
It's sticky aggregated material that sinks pretty quickly. It's the only food delivery system for this vast desert.
But if the ecosystem is so huge, how can it survive on what has to be just thin scraps?
You've hit on the core problem. Only about 1% of the primary production from the surface ever makes it down to the seafloor at these depths.
Just 1%.
Which means life down there has to operate at a completely different pace. Abyssal creatures, they have incredibly slow metabolisms. They often reproduce slowly. They can go long, long periods between meals. They're just masters of extreme energy efficiency.
And then you have organisms that solve the energy problem by just ignoring the sun completely. They create this parallel food chain based on pure chemistry.
Exactly, which happens at the hydrothermal vents.
And this is where things get truly extreme.
This is where the environment is just hostile. These vents are usually near mid-ocean ridges. Seawater seeps into the crust. It gets superheated by magma up to 400 degrees Celsius.
400 degrees.
And then it just blasts back out as this hydrothermal fluid. It's incredibly hot, it's highly acidic, under immense pressure, and it's full of toxic chemicals like hydrogen sulfide.
A chemical cauldron. And this environment powers life through chemosynthesis. How does that actually work compared to photosynthesis?
So photosynthesis uses light to convert CO2 into sugar. Chemosynthesis has the exact same goal, but it uses chemical energy instead of light.
Okay.
These chemotrophic bacteria, they get their energy by oxidizing reduced mineral compounds, like those toxic sulfides pouring out of the vent. They use that energy to create organic molecules from inorganic CO2.
So the bacteria are the foundation. They're the primary producers.
They are.
And the most famous example of this system has to be the giant tube worm, right? Rifty pachyptilla.
Precisely. The tube worm is just a spectacular example of what we call obligate symbiosis. It's amazing. It has no mouth, no gut, and no anus.
No mouth or gut. How does it eat?
It doesn't. It lives in this partnership with sulfur-oxidizing bacteria that are housed inside a special organ called the trophosome.
Wait, the trophosome, can you break down what that is for us?
Yeah, think of the trophosome as the worm's personal internal chemical factory. It basically replaces the job of a stomach and a liver. The worm's plume brings in the chemicals, the sulfide and oxygen, and transports them to the bacteria.
I see.
And the bacteria, using that chemical energy, they fix carbon through the Calvin-Benson cycle and feed the worm directly from the inside. It's a totally closed-loop system, completely independent of the sunlit world.
That's incredible. Moving from that chemical chaos back to the vast, cold plains. Let's switch from food to finding friends, or maybe avoiding enemies. In total darkness, communication has to take a whole new form.
And that form is bioluminescence. You could argue it's the most common form of communication on the entire planet, just based on the sheer volume of the deep sea.
And the mechanism is just beautiful chemistry, isn't it?
It is. It's a chemical reaction. You have a light-emitting molecule, luciferin, and you have oxygen. And that's often accelerated by an enzyme, luciferase.
Okay.
Or sometimes it's all prepackaged in what's called a photoprotein. It's just triggered instantly by calcium ions. That makes the light really rapid and controllable.
And because shorter wavelengths travel better through water, most of this light is blue-green. But the tactical use of this light is what's so amazing.
It's pure strategy. For feeding, you've got the deep-sea anglerfish dangling a glowing lure, a barbel, right in front of its mouth.
The classic example.
Yeah, it attracts smaller fish right into the trap. Or even the tiny cookie cutter shark, which uses a glow on its underside.
Now wait, how does a little glow help a shark that attacks much larger animals like whales?
It's a trick. It's all about counter-illumination. The shark uses these light organs, photophores, to perfectly match the faint blue-green light that's filtering down from way, way above.
So it erases its own shadow.
It erases its silhouette. From below, it just looks like a small fish, which attracts big predators to investigate this easy meal. Then the cookie cutter swoops in, takes a clean circular chunk of flesh, and darts away.
Using light for deception. So what about for defense?
The hatchetfish uses that same counter-illumination, but for camouflage. It's a masterful trick. They have these specialized photophores on their belly, and they can adjust the intensity of their own light to perfectly match whatever ambient light there is.
So they just become invisible to anything looking up from below.
Completely invisible. It's next-level stealth technology, and it's all biological.
And for active defense, the strategies just get weirder.
Oh, they do. The vampire squid, it's actually pretty gentle, but if it's threatened, it'll deploy this startling flash of light and then just disappear into its own arm webbing.
And what about the green bomber worm?
Even more dramatic. When it's attacked, it will actually sacrifice a segment of its own body. It detaches, glows brightly, and acts as a disposable bioluminescent decoy bomb.
Amazing. And there's one species that found a way to bypass this whole blue-green light limitation.
Yes, the deep-sea dragonfish. It's the tactical anomaly. It evolved to both emit and see red light.
And red light doesn't travel well in deep water.
Not at all. It gets absorbed almost immediately, so most abyssal animals are totally blind to it. The dragonfish, though, can light up its surroundings with a red searchlight, spotting red-colored prey that are invisible to everyone else while it stays completely undetectable. It's operating on its own private wavelength.
These incredible adaptations are the result of millions of years of evolution in a place we only recently proved wasn't just a void.
Right. And that journey into the abyss really has to start with the pioneers who first pushed back against that pressure barrier.
Because early on, it was all theoretical, right? We were still dispelling myths.
Yeah, in the late 19th century, people still believed in the azoic zone, this idea that life just couldn't exist below 550 meters because of the pressure and the cold.
But that was eventually disproven, which led to the first really major oceanic voyage.
Exactly. The idea was laid to rest by the Challenger expedition from 1872 to 1876. This was the first dedicated global oceanographic voyage.
On HMS Challenger.
That's right. It traveled for 4 years, covering over 127,000 kilometers. They didn't just collect samples, they basically established the entire field of oceanography.
And what was their biggest takeaway?
They discovered over 4,700 new species. But more importantly, they gave us the first real systematic look at the features of the ocean floor. They mapped the contours of the mid-Atlantic ridge and even took soundings near the Mariana Trench. It was the foundation for everything.
But to get a human eye down there required a machine that could survive that cement truck pressure.
Enter the bathyscaphe Trieste.
Invented by Auguste Piccard, a marvel of engineering.
It's a marvel of counterintuitive engineering. A normal submarine uses air tanks. The Trieste used tanks filled with gasoline.
Gasoline, isn't that, incredibly dangerous? And why gasoline?
It was a brilliant solution to a physics problem. So gasoline is less dense than water, which gives it buoyancy. But the key thing is that, unlike air, gasoline is almost completely non-compressible.
I see.
So as the vessel went down, the immense external pressure wouldn't crush the gasoline tanks. It wouldn't change their volume, which meant it kept its stable lift.
It's like an underwater balloon.
Oh, wow.
How did they control going up and down?
To go down, they flooded water tanks. To go up, they released heavy iron pellet ballast. And it had a fail-safe. If they lost power, electromagnets would fail, the ballast would automatically drop, guaranteeing a slow, safe ascent.
And all that engineering led to the legendary dive of 1960.
January 23, 1960. U.S. Navy Lieutenant Don Walsh and Jacques Piccard, Auguste's son, entered the Challenger deep. This was a 9-hour descent into the deepest known point on Earth.
9 hours, descending into total lightless darkness.
10,915 meters, about 36,000 feet down.
What did they even report from down there?
It was harrowing, but they made it. They famously survived the trip on 15 chocolate bars. But the scientific payoff was huge.
Right.
At maximum depth, through that tiny window, they saw a flatfish and a shrimp swimming on the bottom. And that observation, by human eyes, permanently settled it. Life exists and thrives even at the absolute limits of the ocean.
Today, we're mostly trading that human risk for technology, using these robotic avatars to do the work.
Exactly. Modern exploration is all about separating the human from the machine. We use AUVs, autonomous underwater vehicles, which are pre-programmed to go map and gather data.
That's Sentry.
Right. And ROVs, remote-operated vehicles like Jason, which are tethered to the ship, letting scientists see real-time video, map the terrain, and take really precise samples.
Which brings us to our final and maybe most urgent section, modern conflicts. Now that we can actually reach the abyss, the conversation has really shifted from discovery
to value and vulnerability. The abyssal zone isn't just rich biologically. It's incredibly rich in minerals that are vital for our green energy transition. We're talking about cobalt, nickel, manganese, copper.
And where are these minerals specifically found?
In 3 main formations. Near the hydrothermal vents, you have these seafloor massive sulfides, rich in copper and zinc. On seamounts, you find cobalt-rich crests.
Okay.
But the resources that are most targeted are the polymetallic nodules.
Polymetallic nodules. What are those and where do they form?
There are these potato-sized lumps of metal oxides. They're just scattered across those vast abyssal plains we talk about. They form very, very slowly over millions of years around a little nucleus like a fish tooth or a shell fragment.
And because they're on those flat plains, they're easy targets for extraction.
Exactly. It sounds like this enormous economic resource, right? Essential for batteries, for renewables. But the environmental cost of getting them is where the intense conflict comes in.
The potential damage is catastrophic.
And likely irreversible on any human timescale. Deep sea mining, especially for those nodules, would require these massive collector vehicles that literally strip the top 6 to 20 centimeters of the seafloor sediment.
And in terms of the scale of destruction, what does that mean?
The scale is immense. A single 30-year license could lead to the devastation of, say, 8,000 to 9,000 square kilometers of pristine habitat.
Wow.
And because the abyssal ecosystem is so slow, species live for hundreds of years. They reproduce rarely. Recovery from that kind of strip mining is predicted to take millennia, if it ever happens at all.
And the damage isn't just on the seabed itself. When you strip mine sediment, you create these huge plumes.
Exactly. The mining ships pump the sediment up, or they discharge wastewater back down, and you get these massive sediment plumes that can disperse for hundreds of kilometers.
And they just smother everything.
They settle and smother filter-feeding organisms, like long-lived cold water corals and sponges, far, far outside the actual mining area.
And we can't forget destructive fishing, which still impacts these areas.
Right. Bottom trawling is still a huge threat, especially to seamounts. You're talking about dragging massive weighted nets that just destroy everything in their path. The habitats of species like the orange roughy, which had lived for 200 years, these impacts just stack up.
And finally, there's the big connection between the stable, dark, deep sea and our surface level crisis,
Yeah.
climate change.
The deep sea is one of Earth's largest and most important carbon stores. That carbon is locked away in those vast, stable sediments.
So disrupting them could be a big problem.
It could potentially destabilize that store. And then you have these large-scale geoengineering proposals, like injecting captured CO2 directly into the deep ocean. That risks fundamentally altering the chemistry of an ecosystem that literally thrives on stability.
So this deep dive has taken us from the planet's flattest surfaces, the chemical pathways that fuel life in total darkness, through the daring engineering of the Trieste, and now into this modern dilemma. Do we destroy the ecosystem we just discovered to fuel the progress of the world above?
You know, the abyssal zone represents the ultimate triumph of adaptation. Life down there, whether it's clinging to scraps of marine snow or harnessing chemicals, it developed these unique metabolic mechanisms designed for survival and scarcity.
Especially when it comes to fixing carbon.
Exactly. They are the experts in extracting energy from the impossible.
So as we look to solve our own energy and carbon challenges here on the surface, what can the abyss teach us before we potentially disrupt it forever?
Well, what's fascinating is the sheer biochemical ingenuity down there. I mean, chemoautotrophs use up to 5 different highly efficient CO2 fixation cycles. These are mechanisms totally different from what plants use. So if these organisms adapted these radical enzyme pathways to thrive in these extreme environments, what powerful undiscovered biochemical solutions might they hold for us?
So the answer might be in their genetics, not in the minerals on the seafloor.
It could be. I mean, think about it. Extremely efficient enzymes like carbonic anhydrase, which rapidly converts CO2, could be sourced from these deep-sea extremophiles for radical new biotechnologies. The greatest value of the abyss may not be the metals we want to strip from it, but the genetic code we have yet to truly understand, let alone apply to our own fight against climate change.